Everyone, I'm Dr. Sanjeev Goel, all the way from Toronto, Canada, and I'm thrilled to be here to talk about aging and senescence. I hope you enjoy this talk, and feel free to contact me with any questions that may come from seeing this presentation. So the first thing I want to just talk about is our understanding of what aging is, and we are starting to think of aging as really a balance of our system that maintains us in a healthy state. So we can call that homeostasis. And when the body comes out of balance, that's disease. And you can see that the body's constantly in our cells are constantly in a kind of a war with the outsiding stressors, microbes, viruses, so on and so forth, that could tip us into an out of balance state or disease state. As we age, we think that it becomes harder and harder for the body to maintain a state of equilibrium or homeostasis. And that's why disease becomes more prevalent as we get older. We think that the basic mechanisms of aging revolve around these three big terms: immunosenescence, inflammaging, and cellular senescence. So I'm going to take you through these concepts and explain to you how we're looking at aging now at really a cellular level. We understand that aging, there are definitely changes that are happening with aging in our blood. Everything from different profiles of metabolomes to proteome profiles, which are different, to epigenetic profiles that are different, and methylation. And obviously we have a genetic difference between each other. But this aging shows there are differences in aging, and this is occurring right at the genomic and cellular level. So let's start with this slide here, which talks about how a normal, healthy cell or body responds to an infection. And you can see these Treg cells will have an acute inflammatory response to an infection, and you can see that there'll be a normal rise in inflammation. And then, this is accompanied by local metabolic neuroendocrine changes to address the cause of the inflammation. Body will go and attack, whatever infection is there, and then the inflammation will come back down to the pre-injury status. But when we get older, what it tends to happen here, as you can see with the red line, is that there's that acute inflammation which still gets impacted. But instead of coming back down to the pre-infection levels or incident levels, there is a chronic inflammation which starts to set in. And this leads to a breakdown of tolerance and resulting end organ damage. And this explains why there's lowered host resistance to infections, and why there's, in elderly patients, we're seeing a lower response to vaccines. So in this article, you can see that we understanding that really inflammation is the root cause of etiology of disease across the lifespan. And this occurs for a number of reasons. And we think it's really about senescence now. So the way we think about senescence is that it's really a cellular program that induces a stable growth arrest. And this includes, DNA remodeling, metabolic reprogramming, autophagy, and really the starting of a whole pro-inflammatory cascade or secretome that basically causes all these cellular aging processes to begin. So it's really a the important thing about this senescence is that it's a permanent arrest in the growth of that cell and division. And really the purpose is that to ensure that the damaged or transformed cells do not perpetuate their genomes. Before we get into how senescence is happening, let's talk a little bit about, you know, the thymus. The thymus is the gland um, that produces all the T cells. And what we've found out is that there is an involution of this thymus gland that occurs at a steady rate. And by the age of 50, the thymus gland has really become quite involuted and shrunken. And really, it's quite a interesting marker of the aging of our immune system, this immunosenescence. There are currently three major theories on why this may be happening. And this article by George and Ritter, and it goes into this. But it's one is wear and tear, the idea that over time of just the use of the thymus gland, starts to get old and involutes. Second one is that there's a direct adaptation, means that this is a purposeful uh, mechanism of the organism to involute the gland um, because it's not needed anymore. And the third one is that, that again, that there's disposable soma, means that this idea that we start with a certain amount of gland, and because there's no need anymore for the thymus to be active, it also just involutes. So in any case, we understand now that thymus gland involutes, and that there's a significant uh, change in the way our immune cells function as we get older. And this graph shows the type of changes in the cells, and we'll get into some of these, but you can see that there's a huge difference in the type of cells, uh, that type of cells and quantity of cells of as we get older. But in general terms, it's a decrease in natural killer cells, an increase in memory cells, um, and um, an increase in CD8 and CD4 cells, and decrease in macrophages. So as the innate immune system, T cell immune system gets weaker, the memory B cells get stronger. And I guess that kind of makes sense if you look at that we are constantly being exposed to infections and contact with triggers that stimulate our immune system. And I guess over time, the immune system changes. And that's what we called immunosenescence, which is really an aging of the immune system. And this paper really talks about this again, the inflammation, which is related to, again, to our longevity. And what we are understanding is that the organism experiences a number of these processes, all the way from a DNA level to a cellular level, a systemic level, to keep that inflammation at bay. And when these systems break down, and they do gradually, because we're not built to really uh, live forever. This buildup of inflammation at these different levels that basically causes aging and then death. This one looks at this slide basically shows that as we get older and our system ages, the CD4 to CD8 ratio decreases. Both of the cells increase, but CD8 increases faster, and so that the ratio actually decreases. We can look at this ratio across a number of different diseases, and you can see the ratio decreases with a number of different chronic diseases such as non-AIDS malignancies, Hodgkin's lymphoma, ischemic heart disease, stroke, end-stage kidney disease, and non-AIDS related death. But basically, you can see that all these chronic diseases have a feature of decreased CD4, CD8 ratios. And then we can also look at infections such as CMV, and we can see that one of the characteristics of CMV infections is a lower CD4 to CD8 ratio. And that's accompanied with a number of other phenotypic characteristics, which are, disease and signs of an unhealthy system. They've looked at patients with COVID, and they've shown that those who have the worst and lower levels of CD4 to CD8 ratios will actually end up having more severe and adverse outcomes. So again, this talks to how the immune system and the age of the immune system is directly related to morbidity and mortality. Let's move on. So, as we were talking about, that the aging is really interplay with senescence. So I really love this slide because this diagram is really so good. And what it's saying is that there's a number of factors that can push a cell into senescence. You can see here chronic inflammation. So that's the process of, the chronic disease. Again, aging probably could lead to chronic inflammation, but just the fact of having chronic disease with chronic inflammation will push cells into senescence. There are certain, constant mTOR signaling can push a cell into senescence, or the opposite way, fasting or nutrient deprivation can actually slow down senescence. We have mitochondrial dysfunction, DNA damage. Here's telomere erosion. So as telomeres get shorter, the cells are unable to divide any further, and then they can enter senescence. Epigenetic factors, stem cell exhaustion. An example would be in oocytes of women as they enter menopause. That's really a stem cell exhaustion as a cause of senescence. Here's a diagram showing a healthy physiological cell and a senescent pathological cell, and you can see that there's increased reactive species with decreased SIRT, and the big difference you can see is that there's an impairment in DNA repair, and which then pushes the cell into a senescent state. What's interesting about the senescent state is that the cell begins to secrete what we're called SAS, which are senescence-associated secretory phenotype. So the SASP, the secretome, is basically growth factors, inflammatory cytokines, and chemokines that are released by the senescent cell. And these, again, you can see here, are pro-inflammatory, leading to chronic inflammation, cell proliferation, other cells aberrantly, and immune activation, fibrosis, and so on. So the SASP really, though the cell is not dividing it further, it is secreting all these, in effect, messages and signals to the cells around it, which is causing inflammation and then pushing those other cells into senescent stages. Let's move on from here. And before we're going to move into now some of the therapies that people are looking at, and you can see here that Fecitin, rapamycin, metformin, quercetin, resveratrol, these are all being looked at to treat senescence. We'll go into some of these as time goes on. One of the hallmarks of senescent cells is that the phenomenon of the NAD decreasing as time goes on. You can see that with decreased mitochondrial function and the increase in CD38 and NADAs. So that's a hallmark feature of aging. And if we are to try to address this, this would hopefully address senescence and could be a good strategy. So one of the things that we think that how rapamycin works. So it is normal that cells can move into something called cell arrest, which means that the cell will temporarily stop dividing or go into kind of a quiet, quiescent phase. But with the right stimulation, mTOR being activated, and the right environment, the cell can start dividing again, but then can go back to going to quiet stage if needed. So that's a normal system. But what ends up happening is if there's the factors which are showing of aging, which is constant mTOR stimulation, then it's something called geoconversion. Geoconversion, it's really a irreversible conversion to a senescent cell. So once this happens, that cell becomes senescent, and as I was saying before, it releases SASP, which is hypersecretory, hypertrophic, hyperinflammatory signals to all the other cells around it. So rapamycin tends to prevent this geoconversion, as does fasting. Nutrient deprivation will also do that. But it's interesting that that's how rapamycin is working, by slowing this geoconversion for cells to become senescent. And you can see here, rapamycin inhibits the secretory phenotype of senescent cells by this NRF2 independent mechanism. Dosage, I won't go into too much, but it's meant to be 2 to 6 milligrams once a week, and it does have a number of potential side effects. We have to be careful and to start slowly. Another targeted therapy for senescent cells is called FOXO4, and I'm going to move on from here. Again, this is still in very early days. We've only done trials on mice, so it's not something that people are doing very much. Though one can buy these peptides online, but they're quite expensive. One of the other interesting peptides is called thymosin alpha-1, and thymosin alpha-1 appears to be a way of rejuvenating your immune system. And like I was saying, this immunosenescence shows basically a aging of the T cell ratios, and thymosin alpha seems to bring that back and rejuvenate it. And so this peptide one can get again online. The dose can be anywhere from 1 milligram, 1.6 milligrams injected 2 times a week, and it's a very safe peptide. There's been no really any side effects have been noted from using it. Another peptide that people are using is called MOTS-C, and it basically seems to have a cytoprotective um, effect on reducing senescence. It seems to be working at the level of the mitochondrial DNA, and we know that those people who have more of this MOTS-C, some of these blue zone people tend to have specific types of mitochondrial DNA that have more MOTS-C, and they tend to live longer. This is a very interesting study, and I thought I wanted to end off with the study, which I thought was quite impressive. It talks about a supplement called TA65, which comes from an extract of astragalus, an ancient Chinese herb. And what this study showed was that in humans, it was a double-blind, placebo-controlled, randomized trial, that this supplement TA65 actually decreases this immunosenescent profile of CD8, CD28 minus T cells in humans. And as there's been numerous studies that as we get older, CD8, CD8, CD28 minus T cells increase, and this supplement showed that it decreased this sign of immunosenescent T cells. So I want to end off with this again, this idea that cell arrest is not really the problem here. The problem is this conversion of what is a temporary, cellular arrest of a cell to a permanent arrest. And that has been linked to tumors, atherosclerosis, fibrosis, obesity. And is this what we call conversion of the cell to an aged cell that leads to diseases. And so that is really the crux of the matter. If you can take anything from this talk, take this idea that we need to somehow stop that conversion of normal healthy cells to cells that become converted to senescent cells that then secrete SASP that further aggravates the inflammatory milieu of the cell, leading to further disease. So you can see this cascade that's happening, and this is where people are looking at to impact aging. Well, thank you very much. I hope this was enjoyable and that you took something from it. I apologize, I don't speak Turkish, and I do love Turkey, and I think it's one of the most beautiful countries in the world. So I wish you the best, and you feel free to message me on Instagram or email me. Okay, thank you so much.